Welcome to the Peacademia course on basics of semiconductors. This lecture covers the extrinsic semiconductors. Let's start. By the time you finish this lesson, you will learn the basics of extrinsic semiconductors, impurities used to dope semiconductors, and donor and acceptor energy levels. In the introduction lecture of this course, I talked about the conductors, isolators, and semiconductors. Semiconductors have gained popularity in electronics industry mainly because their electrical properties can be controlled by doping. But what is doping? To address this question, let's look at this two-dimensional silicon lattice. This is just an example. If all the atoms are made of the silicon, we call it intrinsic. In the doping process, some of the silicon atoms are replaced by another atom. In other words, we add impurities to the intrinsic semiconductor. A semiconductor with impurities is called doped semiconductor or extrinsic semiconductor. To make a doped semiconductor, am I allowed to introduce any impurity to an intrinsic semiconductor? While you can add any impurity you want to an intrinsic semiconductor to gain proper electrical properties, you must be careful of what you add as impurity. So a simple answer to the question is no. Let's take a look at the periodic table of the elements. Imagine that I have an intrinsic silicon semiconductor. Silicon is a group 4 semiconductor because it has 4 valence electrons. Silicon is normally doped by either group 3 or group 5 semiconductors. I discussed the reason for this choice in part 2 of this lecture. Group 3 semiconductors have 3 valence electrons and group 5 semiconductors have 5 valence electrons. Let's first impure the intrinsic silicon by a group 5 semiconductor such as phosphorus. To do so, what I need to do is to replace a silicon atom with the phosphorus atom. The phosphorus atom has 1 more electron in its valence shell compared with the silicon atom. As a result, unlike the other 4 electrons bonded covalently to the adjacent silicon atoms, the 5th electron is bonded to phosphorus atom by the electric field exerted from the phosphorus nucleus. Relative to the covalent bond, this electric field bonding is weak. In the energy band diagram at 0 degrees Kelvin, all the states associated with silicon atoms in the valence band are occupied by electrons, and the conduction band is empty. By doping phosphorus to the silicon, a new energy level appears in the energy band diagram. This energy level corresponds to the electric field bonding the 5th electron to the phosphorus atom. The difference between this energy level and the bottom of the conduction band is called the ionizing energy and is shown by delta ED. At higher temperatures, let's say at the room temperature, some intrinsic carriers are generated. For silicon, the concentration of intrinsic carriers is 10 to the power of 10 atoms per centimeter cube. Due to relatively large energy gap of silicon compared with delta ED, there are still too many states in the valence band remained occupied. However, because the ionizing energy is relatively very small in comparison with the band gap of silicon, most of the electrons in this energy level go to the conduction band at room temperature. Since in this case, each phosphorus atom is donating 1 electron, we call the phosphorus atoms donors, and this energy level is called the donor energy level and is shown by E sub D. Delta ED is the difference between EC and ED. Because each donor atom is losing an electron, it becomes a positive ion. This is why delta ED is sometimes called ionizing energy. If the concentration of donors is shown by N sub D, the concentration of those donors that are ionized is N plus sub D. depending on the ionizing energy, N sub D is or is not equal to N plus sub D at a given temperature. Now, by looking at the energy band diagram, the concentration of negative charge carriers for electrons in the conduction band is much larger than that of positive charge carriers or holes in the valence band. We call this doped semiconductor a negative type or N-type semiconductor. Let's impure the intrinsic silicon by a group 3 semiconductor such as boron. To do so, what I need to do is to replace a silicon atom with a boron atom. The boron atom has one less electron in its valence shell compared with the silicon atom. As a result, the boron atom is covalently bonded to 3 adjacent silicon atoms, but not the fourth one. Therefore, a hole is generated. In the energy band diagram at 0 degrees Kelvin, the valence band of silicon is full and the conduction band is empty. When boron is doped into silicon, a new energy level close to the top of the valence band appears. This energy level corresponds to the holes generated as a result of doping boron into silicon. At higher temperatures, let's say at room temperature, because the energy gap between the new energy level and top of the valence band is so small, most of the states or holes in the new energy level are filled by electrons coming from the valence band. Moreover, some electrons go to the conduction band. The energy level associated with dopant boron is called the acceptor energy level and is shown by E sub A. The reason for this naming is that at this energy level there are holes or empty states accepting electrons from the valence band. Moreover, boron as a dopant is called an acceptor. Delta EA is the difference between EA and EV. Delta EA is sometimes called ionizing energy. After an electron is accepted, the boron turns into a negative ion. If the concentration of acceptors is shown by N sub A, the concentration of those acceptors ionized is N minus sub A. Depending on the ionizing energy, N sub A is or is not equal to N minus sub A at a given temperature. Since in this case, the number of positive charge carriers or holes is much higher than negative charge carriers or electrons, we call this doped semiconductor a p-type semiconductor. In this lecture, I talked about the basics of extrinsic semiconductors, the impurities we can use to dope intrinsic semiconductors, and donor and acceptor energy levels. In the next lecture, I will show other aspects of extrinsic semiconductors. Thanks for joining this lecture of Peacademia.